The average male drinks 2 liters of water when active outdoors, with a standard deviation of 0.7 liters. You are planning a full day nature trip for 50 men. 50 men, and will bring 110 liters of water. What is the probability that you will run out of water? So let's think about what's happening here. So there's some distribution of how many liters an average man needs when they're active outdoors. And let me just draw an example. It might look something like this. So they're all going to need at least more than 0 liters. So this would be 0 liters over here. The average male, so the mean of the amount of water a man needs when active outdoors is 2 liters. So 2 liters would be right over here. So the mean is equal to 2 liters. It has a standard deviation of 0.7 liters, or 0.7 liters. So the standard deviation, maybe I'll draw it this way. So this distribution, once again, we don't know whether it's a normal distribution or not. It could just be some type of crazy distribution. So maybe, some people need almost close to, well, everyone needs a little bit of water, but maybe some people need very, very little water. Then you have a lot of people who need that. Maybe some people who need more, and maybe no one can drink more than maybe this is like 4 liters of water. So maybe this is the actual distribution, and then one standard deviation is going to be 0.7 liters away. So this is 1.7 liters so this would be 1 liter, 2 liters, 3 liters. So one standard deviation is going to be about that far away from the mean. If you go above it, it'll be about that far if you go below it. So let me draw. This is the standard deviation. That right there is the standard deviation to the right. That's the standard deviation to the left. And we know that the standard deviation is equal to, I'll write the 0 in front, 0.7 liters. So that's the actual distribution of how much water the average man needs when active. Now, what's interesting about this problem, we are planning a full day nature trip for 50 men and will bring 110 liters of water. What is the probability that you will run out? So the probability that you will run out, let me write this down. The probability that I will or that you will run out is equal or is the same thing as the probability that we use more than 110 liters, use more than 110 liters on our outdoor nature day, whatever we're doing, which is the same thing as the probability. If we use more than 110 liters, that means that on average, because we have 50 men, so 110 divided by 50 is what? That's 2 point. Let me get the calculator out just so we don't make any mistakes here. So this is going to be the calculator out. So on average, if we have 110 liters, and it's going to be drunk by 50 men, including ourselves, I guess, that means that it's the we would run out if on average more than 2.2 liters is used per man. So this is the same thing as the probability of the average, or maybe we should say the sample mean, or let me write it this way, that the average water use per man of our 50 men is greater than, or we could say greater than or equal to, let me say greater than, well, I'll say greater than, because if we write on the money, then we won't run out of water, is greater than 2.2 liters per man. So let's think about this. We are essentially taking 50 men out of a universal sample. And we got this data. Who knows where we got this data from, that the average man drinks 2 liters, and that the standard deviation is this. Maybe there's some huge study, and this was the best estimate of what the population parameters are. That this is the mean and this is the standard deviation. Now we're sampling 50 men. And what we need to do is figure out essentially what is the probability that the mean of this sample, that the sample mean is going to be greater than 2.2 liters. And to do that, we have to figure out the distribution of the sampling mean. And we know what that's called. That's the sampling distribution of the sample means. And we know that that is going to be a normal distribution. We know a few of the properties of that normal distribution. So this is the distribution of just all men. And then if you take samples of, say, 50 men, so this will be, let me write this down. So down here, I'm going to draw the sampling distribution, distribution of the sample mean of the sample mean when n, so when our sample size is equal to 50, when our sample size is 50. So this is essentially telling us the likelihood of the different means when we are sampling 50 men from this population and taking their average water use. So let me draw that. So let's say that this is the frequency, and then here are the different values. Now, the mean value of this, the mean, let me write, the mean of the sampling distribution of the sample mean, this x bar, that's really just the sample mean right over there, is equal to, it's going to be equal to, if we were to do this millions and millions of times, if we were to plot all of the means when we keep taking samples of 50 and then we were to plot them all out, we would show that this mean of distribution is actually going to be the mean of our actual population. So it's going to be the same value. I want to do it in that same blue. It's going to be the same value as this population over here. So that is going to be 2 liters. So we're still centered at 2 liters. But what's neat about this is that the sampling distribution of the sample mean. So you take 50 people, find their mean, plot the frequency. 50 people, find the mean. This is actually going to be a normal distribution regardless of, this one just has a well-defined standard deviation of mean. It's not normal. Even though this one isn't normal, this one over here will be. And we've seen it in multiple videos already. So this is going to be a normal distribution. And the standard deviation, and we saw this in the last video, and hopefully we've got a little bit of intuition for why this is true. The standard deviation, actually maybe put it a better way, the variance of the sample mean is going to be the variance. So remember, it's going to be, this is standard deviation. So it's going to be the variance of the population divided by n. And if you wanted the standard deviation of this distribution right here, you just take the square root of both sides. If you take the square root of both sides of that, we have the standard deviation of the sample mean is going to be equal to, square root of this side over here, is going to be equal to the standard deviation of the population divided by the square root of n. And what's this going to be in our case? We know what the standard deviation of the population is. It is 0.7, 0.7, 0.7. And what is n? We have 50 men, so it's 0.7 over the square root of 50. Now let's figure out what that is with the calculator. So we have 0.7 divided by the square root of 50. And we have 0.09, I'll say 0.098 was pretty close to 0.99. So I'll just write that down. So this is equal to 0.099. That's going to be the standard deviation of this. So it's going to have a lower standard deviation. So it's going to look, the distribution is going to be normal. It's going to look something like this. So this is 3 liters over here. This is 1 liter. 1 liter. The standard deviation is almost a tenth. So it's going to be a much narrower distribution. It's going to look something, I'm trying my best to draw it. It's going to look something like this. Something like this. You get the idea. Where the standard deviation right now is almost 0.1. So it's 0.09, almost a tenth. So it's going to be, something, one standard deviation away is going to look something like that. So we have our distribution. It's a normal distribution. And now let's go back to our question that we're asking. We want to know the probability that our sample will have an average greater than 2.2. So this is the distribution of all of the possible samples, the means of all of the possible samples. Now, to be greater than 2.2, 2.2 is going to be right around here. 2.2 is going to be right around here. So we essentially are asking, we will run out if our sample mean falls into this bucket over here. So we essentially need to figure out what is, you can even view it as, what's this area under this curve there. And to figure that out, we just have to figure out how many standard deviations above the mean we are, which is going to be our z-score. And then we could use a z-table to figure out what this area right over here is. So we want to know when we are above 2.2 liters. So 2.2 liters, 2.2, we could even do it in our head. 2.2 liters is what we care about. That's right over here. That is, our mean is 2. So we are 0.2 above the mean. Above the mean. above the mean. And if we want that in terms of standard deviations, we just divide this by the standard deviation of this distribution over here. And we figured out what that is. The standard deviation of this distribution is 0.099. So if we take, and you'll see a formula where you take this value minus the mean and divide it by the standard deviation. That's all we're doing. We're just figuring out how many standard deviations above the mean we are. So you just take this number right over here, divided by the standard deviation, so 0.099 or 0.099. And then we get, let's get our calculator. And actually we had the exact number over here. So we could just take 0.2. We could just take this 0.2 divided by this value over here. And on this calculator, when I press second answer, it just means the last answer. So I'm taking 0.2 divided by this value over there. And I get 2.020. So that means that this value, or I should write, this probability is the same probability of being 2.02 standard deviations, or maybe I should write it this way, more than, let me write it down here where I have more space. So this all boils down to the probability of running out of water is the probability that the sample mean will be more than just the 50 that we happen to select. Remember, if we take a bunch of samples of 50 and plot all of them, we'll get this whole distribution. But the group of 50 that we happen to select, the probability of running out of water is the same thing as the probability of the mean of those people will be more than 2.020 standard deviations above the mean, above the mean of this distribution, which is actually the same distribution. So what is that going to be? And here we just have to look up our z-table. Remember, this 2.02 is just this value right here, 0.2 divided by 0.09. I just had to pause the video because there's some type of fighter jet outside or something. Well, anyway, hopefully they won't come back. But anyway, so we need to figure out the probability that the sample mean will be more than 2.02 standard deviations above the mean. And to figure that out, we go to a z-table, and you can find this pretty much anywhere. Usually it's in any stat book or on the internet, wherever. And so essentially we want to know the probability. The z-table will tell you how much area is below this value. So if you go to z of 2.02, that was the value that we were dealing with, right? Yeah, 2.02. It was, so you go for the first digit. We go to 2.0, and it was 2.02. 2.02 is right over there, right? So we had 2.0, and then the next digit you go up here. So it's 2.02 is right over there. So this 0.9783, let me write it down over here. This 0.9783, I want to be very careful, 0.9783. That z-table that's not this value over here. This 0.9783 on the z-table, that is giving us this whole area over here. It's giving us the probability that we are below that value, that we are less than 2.02 standard deviations above the mean. So it's giving us that value over here. So to answer our question, to answer this probability, we just have to subtract this from 1, because these will all add up to 1. So we just take our calculator back out, and we just take 1 minus 0.9783 is equal to 0.0217. So this right here is 0.0217. Or another way you could say it, it is a 2.17% probability that we will run out of water. And we are done. Let me make sure I got that number right. So that number, it was, yeah, 0.2017. Right. So it's a 2.17% chance we run out of water.